Chapter 8, Section 1, Linear Momentum and Force. Momentum is another one of these terms that we use in everyday life that the way we use it is similar to its definition in physics. We think of a large object moving quickly as having a large amount of momentum, whereas a small object moving slowly has a smaller amount of momentum. Momentum is actually defined in terms of those two quantities. We give it the symbol P, and we say momentum is equal to mass times velocity. Because it is mass times velocity, note that it is a vector, so momentum has magnitude and direction. It's proportional to the mass and proportional to the velocity. It has units of kilograms and meters per second. It doesn't have a special name assigned to the units. I've noticed that my software cuts off some of my symbols, so I've got to fix that on here. This is a summation sign. Newton's second law, the sum of all the forces on a system or on an object is equal to mass times acceleration of that object. Actually, Newton's second law is stated in terms of momentum rather than in terms of mass and acceleration. Newton's second law says that the sum of all the forces is equal to the change in momentum of the system per time. Now we can see where F equals ma comes from if we plug in the definition of momentum. As long as mass is constant, we can take it outside of the change operator, or the delta, and so we have mass times delta V over delta T is equal to the sum of all the forces. And note that change in velocity over change in time is just simply acceleration. So, when mass is constant, change in momentum over change in time simplifies to mass times acceleration. Given the definition of momentum and Newton's second law, there's another term we want to define, and that term is impulse. So if we take Newton's second law, which says that the net force equals the change in momentum over change in time, and rearrange it, simply solve for change in momentum. The change in momentum is something we call impulse, and it's equal to the net force times delta T. Let's take a look at an example. In your textbook, starting on page 287, example 8.2 deals with a problem in which a tennis ball is struck by a tennis racket, and the tennis ball leaves the tennis racket at a speed of 58 meters per second. Given the mass of the tennis ball and the time during which the tennis racket is in contact with the tennis ball, your textbook goes through and calculates the average force on the ball. Now let's ask the question, what if the ball, after leaving the tennis racket, flies into the net and is brought to a stop in the net? But it's brought to a stop in a different amount of time. So if we assume that the ball is brought to a stop in 1/10 of a second, we want to calculate the average force by the net on the ball. So let's draw a picture of what's happening first. So here's the situation described in example 8.2. A tennis ball initially at rest, approximately at rest, is struck by a tennis racket. The tennis racket pushes on the ball for 5 milliseconds, and in that time imparts the ball with a speed of 58 meters per second. From this, your textbook calculates that the average force on the tennis ball is 660 newtons. Now let's assume the tennis ball runs into the net and the net brings it to a stop in 1/10 of a second. So it initially has a speed of 58 meters per second. After 1/10 of a second, it has a speed of 0. And we want to calculate the average force on the ball by the net. The tennis net exerts an average force of 33 newtons on the tennis ball to bring it to rest in 1/10 of a second. Compare that to the 660 newtons produced by the tennis racket on the ball to get it up to 58 meters per second. The difference here is the time involved. If we take a look at the force as a function of time, what we'll see is in the case of the tennis racket acting on the tennis ball, the force goes extremely high over a short amount of time, whereas the net produces a smaller force, but it lasts for a longer amount of time. But in both cases, the impulse or the change in momentum is the same, other than a minus sign. In the plot of force versus time, what that means is the area under the curve is the same. The area under the curve for the tennis racket will be the same as the area under the curve for the net. And so for a given impulse, I can have a large force over a small amount of time, and that will give me a certain size impulse, or I can have a smaller force if I increase the amount of time over which it acts. This is the concept in crumple zones in cars or airbags to protect passengers in a collision. You want to increase the amount of time over which the person is brought to a stop to decrease the amount of force that the person experiences. You can bring the person to a stop in a very short amount of time, but it will require a huge amount of force, which may be damaging to the person's body. If you can increase the amount of time for the impulse, then you can decrease the amount of force that's needed to produce that impulse. Chapter 8, Section 3 deals with conservation of momentum. Again, Newton's second law says that the sum of the forces on a system will equal the change in momentum of that system divided by the change in time. Now, if I look at this equation, what happens if the net force is 0? If the sum of all the forces is 0? Well, if the net force is 0, then that means the change in momentum will be 0, or momentum will be constant. Now let's look at this in the context of a collision. Here I have 3 pictures showing different times in which mass 1 and mass 2 are going to collide. Here's the situation. Mass 1 is traveling at a speed v1, mass 2 is traveling at a speed v2, and we're assuming that v1 is greater than v2. So mass 1 will catch up to mass 2 and collide with mass 2. So in the first picture, mass 1 is approaching mass 2. They're both traveling to the right. In the second picture, they're colliding. Mass 1 runs into mass 2. When that happens, mass 1 will exert a force on mass 2. And that's represented here by F21. This is the force on mass 2 by mass 1. But Newton's third law says that for every force, there's an equal and opposite force. So the force on mass 2 by mass 1 will be equal and opposite to the force on mass 1 by mass 2. Or in other words, F21 is equal to negative F12. That's just an application of Newton's third law. After the collision, mass 1 bounces off of mass 2, and they each have new velocities. Now, in this situation, my system is the combination of mass 1 and mass 2. So if I add up all of the forces, if I sum all the forces on the system, F21 and F12 will cancel out, meaning the net force will be 0. Well, if the net force is 0, that means the change in momentum is 0. So the change in momentum of my system is 0. Change in momentum is P final minus P initial, which means that the initial momentum will equal the final momentum. Chapter 8, Section 4 deals with elastic collisions in one dimension. Again, we have Newton's second law. Sum of the forces equals change in momentum over change in time. And in collisions, if our system involves the two things that are colliding, then the sum of the forces will be 0, because the forces between the objects during the collision will cancel out by Newton's third law. We have the situation where the sum of the forces equals 0, and therefore the change in momentum will be 0, which means initial momentum equals final momentum. We're going to define elastic collision as a collision in which kinetic energy is conserved, meaning that there's no loss of kinetic energy. If I have a one-dimensional collision where I know everything that's happening before the collision, meaning I know the values of the masses and I know how fast things are moving, after the collision, I will have two unknown values: the velocity of mass 1 after the collision and the velocity of mass 2 after the collision. Energy conservation gives me one equation with two unknowns. But if it is an elastic collision, I have a second equation that I can use to solve for velocities. By knowing that it is an elastic collision, I know that the kinetic energy before the collision will equal the kinetic energy after the collision.